This video serves as a quick introduction to our measurements of small vertical distances by focus scanning using a microscope. Here we use an inverted microscope set up for reflected light imaging. I'm using glass powder as a token specimen. To set up Köhler elimination, I first find the specimen and focus on it. Next, I'm closing the field stop. As we see, the outline of the aperture appears sharp and in focus at the same time as the specimen. This isn't surprising because the reflected light image of the field stop is produced at the top surface of the glass cover slip, which is also the surface on which the glass powder rests. We usually can center the field stop, but its position along the optical axis is fixed, unlike the position of the condenser that we need to adjust properly in transmitted light imaging. Closing the A stop too far reduces the amount of light that illuminates our specimen. Generally, the optimal opening of the A stop should ensure that we are utilizing the full numerical aperture of the objective. Now I'm focusing downwards, moving the objective away from the specimen plane. After a short distance, the image of the field stop comes into focus again, even though the specimen is not in focus. At this point, the objective's focal plane coincides with the underside of the cover slip, which is another optical interface that produces a reflected light image of the field stop. Focusing down further or back up and above the specimen plane confirms that there are no other interfaces at which an image of the field stop could form. Now, to provide an accurate readout of the position of the objective during this kind of focus scanning, we can use a piezoelectric actuator that translates the objective vertically. One of the displays at the front of the controller of this actuator shows the current position of the objective in microns. We can also automate focus scanning by providing an analog voltage input to the piezo controller. Here we use a triangular waveform supplied by the waveform generator shown at the top to drive repetitive linear up and down translations of the objective. Being able to keep track of the position of the objective raises an interesting question. Can we use the setup to measure vertical distances? For example, the distance between the top and bottom surface of a cover slip. In principle, this should be possible. But we need to be careful and ask ourselves, does the objective's focal plane always travel the exact same distance as the objective itself? Let's try such a measurement with a number 1.5 cover slip. We use the focus evaluation tool of our camera software to first determine the objective position at which the underside of the cover slip is in focus. At this point, the piezo controller reports the objective position as 53.4 microns. Next, we move the objective upwards until the upper side of the cover slip is in focus. Here we go. We arrived at an objective position of 171.3 microns for a total travel distance of 118 microns. This is actually quite different from the known thickness of number 1.5 cover slips, which is about 170 microns. Let's double check what we found with the number 1 cover slip. The known thickness of this cover slip is around 150 microns. Again, our result is not what we might have expected. In the next video, we will systematically explore what is going on.